Hi, this is Abe and I'm going to introduce you to the idea of definite integrals. Okay, so first up, definite integrals are for finding areas under curves. So, a good start. And so, as an example, I want to find, let's say, the area under this curve here on the left. I'm going to do this. I want this area. Okay? Now, that's at so from x equals a to x equals b. Okay, so prior to this, you would have used some method to approximate the area under a curve. If you're not sure how to do that, feel free to check out my video on that. But essentially what you've done, well, what you would have done in the past is you sort of drew rectangles like this, right? And you tried to approximate area that way. Now, it's an okay method of doing things, but obviously it's not very precise. So, let's see if we can improve things. Remember that the formula, right, for approximating an area under a curve, or one of the formulas, this is the left endpoint estimate formula, looks a bit like this. F of x1 plus a whole lot plus f of x to the n minus 1. Like that, right? And you'd remember that x0 is just this first bit here, x1, x2, so on, right? Okay, so the idea is this. The idea in definite integrals is, what if our n got very large? So in other words, what if we were able to approximate this area by using infinite strips? And I suppose if you had infinite strips, they'd be infinitely thin, right? So I'm going to try to get this happening on the right. And so your strips will just look like this, and so on. And you'll see that if your strips are only this wide, that your estimate is going to be pretty accurate. So the idea is basically that you'll get this going on, that you can get a better area if you take a limit. Oh, limits. Thought you were past them. Limit as n runs to infinity of our area approximation formula. So this is not strictly mathematically all true, but pretty much it's very good for just the ideas part, so we can assume this is all true. So what you want to do is make our strips super thin, like we've done here, and you add up all these areas and your area estimate will be better. So a nice way to write this long limit is as follows. You can do this. You can say, right, remember on our last page we said that A is roughly equal, well, it actually is going to be equal, the limit as n runs to infinity of our approximation, right? The more strips you have, the more accurate your approximation is. Z minus 1, like that. This B is not coming out very well. Okay, and that, there's a nice way to write that. It looks like this. And the way you say this is the integral of f of x evaluated between a and b. So, quick diagram. If this is my curve, f of x, and this is point A, and this is point B, then this area inside is represented by that expression. The integral of f of x evaluated between A and B. So this essentially just means find f of x, or get f of x, and this expression represents this area under f of x, or area between f of x and the x-axis, from x equals A to x equals B. Now, this funny integral sign, this thing here, must be present, and also the dx must be present. Think of them as brackets of sorts. Without those things, this expression makes no sense. I'm saying this because a lot of students don't like to write these things in, but you have to, otherwise you don't have an integral. Okay, so the next question is, how do you evaluate this, right? How do you find this integral of f of x evaluated between A and B without drawing pictures and trying to estimate areas? Well, it uses a technique called anti-differentiation. And as you might imagine, it's the opposite of differentiation. And in the next few videos, I'll be explaining exactly how that works. So for now, hope you've enjoyed yourself. I'll see you next time.